Okay, in this video, I will mention or just add a small, tiny note about order of reaction, first order and zero order, that I want you to keep in mind and just use it when we are talking about different models, just to make sure if you got it or you understand it. So if we go back to zero order, um, let's say, rate of reaction, we mentioned earlier in the zero order video the equation, the differential equation that we have, what we did to have the profile, and then we draw the profile. And if you remember what we were drawing the amount or concentration versus time, right? And again, just to remind ourselves about a certain time, okay? Or just let's write it down. At certain time, amount of the drug, and we said that it could be amount or concentration, the same if we are talking about um, constant volume distribution. So it will be, or volume, just let's call it volume in here at this point. So it could be a concentration if we divide the amount over volume. So it will be concentration at certain time equal initial concentration, initial concentration multiplied to the time, right? And when we draw this or that profile, it was again on rectilinear profile, we had amounts, certain time versus time, and we had it as this linear because we have a linear equation here, and this is our slope. So we use the slope to determine the zero order rate constant, and we have this as the y-intercept, okay? And for sure, similar profile would be here for concentration at certain time versus time. We will have this. The only difference that you will have here C naught, but the slope won't change. It would be equal minus K naught. The question is, and again, just to remind ourselves before I ask you the question, what is the equation, the initial equation that we have for zero order reaction? If you remember, it was dA over dt, okay, minus K naught, okay? So this is the rate of decrease in the amount over as amount decrease over time, and it was equal to first zero order rate constant, okay? So if I want to ask you the question now, if I want to draw not the amount, not the concentration, I want to draw rate of decrease in the amount A, and as we mentioned before, let's say example, it's rate of elimination as in one example in kinetic versus concentration of the drug or amount of the drug remains in the body. According to this, what would be the relationship here? Let's write it here again to see it. What would be the relationship here? Again, the rate would be equal to constant. So the profile would be constant. Whatever the amount that we have at certain time or the concentration that we have at certain time, the rate won't change with the concentration or time because it's equal constant term, that is the zero order rate constant. So this is important to remember, okay? If we go to first order kinetic, or let's call it for now first order rate, If we remember the differential equation that we have, dA over dt, which is equal to minus k, right? First order multiplied to the amount certain time at certain time. And we say that the rate of decrease in A is proportional to the amount that we have, right? And this is first order rate constant. When we were drawing the profiles, we had, before we draw the profile, we have different equation, either the exponential one, which is amount at certain time equal initial amount, E minus K, multiplied to the time. The second one was log transformed, A at certain time, log initial amount minus K over 2.303 multiplied to the time, right? Or the third, which was len transformed, so the equation in the len term minus K multiplied to the time. And we had four different profiles according to whatever we are drawing, and we either draw, and you will review those four profiles in our first order video for the rates or orders of reactions. We either draw A certain time versus time, A certain time versus time on either rectilinear profile or semilog profile, or we draw log amount versus time on rectilinear graph, or len amount at certain time on versus time on rectilinear graph, right? And you can go and review those profiles, but I will just draw them and you can review the intercept and the stuff for each one of them. And this is linear for sure, okay? It was shown not, but it's linear, okay? And the same thing, we said that we can have the same equation in concentration term by just dividing the amount over the volume to have the concentration, right? So I will ask you the question again, taking into consideration that our differential equation for first order kinetic equals dA over dt minus k multiplied to the amount. Okay, so if I want not to draw the amount or concentration versus time, or its log or len transformation versus time, what if I want to draw rate of decrease in A, okay, versus the concentration of the drug or amount at certain time? Again, rate versus amount at certain time, or rate of concentration decrease versus concentration. What would be the relationship? Okay, we said that if we are talking about first order kinetic, the relationship is proportional, directly proportional to the amount of concentration. So it would be linear. It's directly proportional as the concentration of the drug or the amount of the drug in the body increase, the rate would be increasing. If the amount or concentration of the drug in the body decreased, then the rate would decrease. Okay, so we have a directly a proportional relationship, which why we call first order kinetic as linear kinetic because of that, because the rate of, in this case, decrease in the amount or concentration in a proportional, direct proportional relationship with the concentration or amount. And in one of the examples in kinetic, let's say rate of elimination of the drug, it's proportionally related to the amount or concentration of the drug in the body at certain time. So that's why we call it linear kinetic. And that what you can see in the table that you have at the end of your slides, in which if we are talking about zero order kinetic, the versus first order kinetic, it's the same thing that you can see in the profiles that that I draw for you as rate versus concentration or amount, because as the amount of the drug, let's say in milligram, is decreasing with time, okay, if the amount is decreasing, the rate of decrease over time is what? Is not changing. It's constant. That's why we have this profile, okay, between rate versus concentration. But if the amount of the drug is decreasing with time, okay, in first order kinetic, the rate would also be decreasing in a proportional way. So that was my note for the first order and zero order kinetic. If we are drawing or looking at the relationship between the rate and the amount of concentration, amount or concentration, rather than the concentration or amount versus time. So just keep this in mind because it's very important, and good luck.